welcome back to today's video. We are going to continue on with multivariable calculus, and today's video we will focus on finding volume of a solid region in 3D space using integrals, specifically triple integrals, z-simple, and polar coordinates. So let's get started. So for this question, we are trying to determine the volume of a solid region W in R cubed, defined by the inequalities. So before we get started, we know that we have a general sense that we are going to take triple integral. The reason for that is because we see there's z and there's also xy. But before we get into the integration, we must also understand what's happening. And a useful way to understand that is through graphing. So for this first inequality that we see, it is in terms of z. So if we were to draw this in 3D dimensions, remember we have the three different axes. There's the x-axis, the y-axis, and the z-axis. And it says that z is between 0 and square root 1 minus x squared minus y squared. So what this is going to look like, and apologies for my not so nice drawing, is that we're going to have something like a semicircle kind of shaped region. And we can see that this region would be basically positive only, because we know that z has to be greater than 0, and then we are bounded by this here. And to further make more sense of that, let's move on to looking at the other inequality that the problem gives us. So we have x squared plus y squared less than or equal to 1. So when we see this, we see that there's only x and y values. So what we can do is we can now then change our 3D plane into a 2D plane represented with just x and y. And what this is going to look like is, if I were to change the inequality to an equal sign, we can clearly see that it is just a circle with radius 1, right? Because square root of whatever number here, in this case it's 1, it's just 1, so our radius is 1. And so if what's happening here is we're essentially looking from the point of view of the z-axis. So let's say this is, our eyes are here and we're looking down upon the z-axis, and this is what it looks like from the top. So if that makes sense, we kind of have like a little circle here, and we are looking from this perspective. And what we're trying to determine right now is the region. So it says that x squared plus y squared has to be less than or equal to 1, so that means it has to be in somewhere inside this circle. But we're also given two other inequalities, so let's take a look at that. So we have x plus y greater than or equal to 0. Again, I want to set this equal to 0 for the sake of graphing, and we get a linear function that we're familiar with, which is y equals to negative x. And it says that x squared plus y squared has to be greater than or equal to 0. So if it's greater than or equal to 0, then we can see that y has to be greater than or equal to negative x. So first, if we go to graph y equals to negative x, we have this linear line here, and it says that y has to be greater than negative x, so that means it will be somewhere here. So that further condenses our region. And last but not least, it says that y has to be greater than 0, so that means y has to be positive. So meaning that our shaded region will look something like this, where all y values are positive, and it's also bounded inside the circle and as well as above the line. So this satisfies all of our inequalities above. And so the next step that we're going to be doing then is to actually integrate and write our integral. So first of all, we can notate our integral. Remember that the solid region is called W, so thus we have W dV. That's how you notate it. And in a sense, what's happening is we have the three axes, right? There's z and x and y, right? Z, x, and y. And so what's going to happen is, to condense the integral, we want to break it down. So we would first separate the first two integrals outside, and that's just the domain. And then inside we'll have another integral. And what we want to do in this case, so there's different ways to approach this, but since we're clearly given the z inequality, then we know that we can be integrating dz first. And the reason we have no function inside is because we're calculating the volume, and that's essentially the same as saying integral of 1 dz, and then the rest would be dy and dx, or dx dy. It depends on, it doesn't really matter which order in this scenario, but we want to have dz in our most inner integral. And then for that, we want to also know our boundaries, right? When we integrate, we want to, especially when we're determining the volume, we want to know the boundaries. And right now we can just focus on the inside integral, which is with respect to dz. And for the integral, we can clearly see that the first inequality we're given is that z is literally between 0 and 1, square root 1 minus x squared minus y squared. So we can just plug in our boundaries just like that. So I'll be moving these so we can put in our boundaries. So it's from 0 to square root 1 minus x squared minus y squared. And so if we were to do this, if we were to first calculate that, the integral of 1 in this case would just be z. So essentially we are finding the integral, and then we are going to be plugging in our boundaries. And in this case, it's just going to leave us with square root 1 minus x squared minus y squared minus 0, but the 0, we don't have to write that down. So then we're left with this. So this is just like any other double integrals that we have seen before. And now the next step is to solve this. And one way to easily solve this, looking at what we're already given, is to use something called polar coordinates. And basically, polar coordinates are very useful when in multivariable calculus, they're useful when we are trying to rewrite a 2D point using radius r and angle theta. So what this means is we have some formulas that are very useful is when we use polar coordinates. We are essentially replacing x and y and substituting them into other variables. And a general formula is that x is r cosine theta and y is r sine theta. And if you want to know what r squared is, that is essentially x squared plus y squared, right? Because r squared cosine squared theta plus r squared sine squared theta. If we simplify that, we have r squared cosine squared theta plus sine squared theta, and this is just equal to 1. So that's a direct proof of r squared equals to x squared plus y squared. And so given r squared, we can also know what r is, which is just the square root of x squared plus y squared. And so this is very useful, and note that we have the two variables r and theta in this case. And the general formula for polar coordinates is we have double integral of a function, and we can rewrite that in polar coordinates to be f of, in this case, x is r cosine theta and r sine theta. And the dA will then be changed into r dr d theta. And so in this case, dA is equal to r dr d theta, and that's a very important formula to know. So now that we have this kind of general formula, let's try and change this into polar coordinates. So if I were to do polar, I have the two integrals, I keep them there, and I replace x as r cosine theta and y as r sine theta. And if I were to do that, I easily simplify my answer to get 1 minus r squared. And for the dy and dz, we then replace them with r dr d theta, just like that. And then our next step is to find the boundaries for that. So we are given the inequalities, and the reason we're doing polar coordinates is because we can easily see that we can change these into r. If I were to do this just based on picture, I can see that our r, or our radius, is going to be between 0 and 1, right? Because our radius is 1, so it could stretch from 0 to 1, stretch from 0 to 1, something like that, if we just look at the picture. If we were to look at what we're given here, we can also see that since we know x squared plus y squared is equal to r squared, we know that r squared is going to be less than 1, which is the same as saying r is less than 1, something like that. And so just from the equation 2, we can find out the boundaries. For theta, here we can easily see from our picture that it can be stretched from 0, and it goes from 0, and the angle here goes from 0 to 3 pi over 4. Just like the unit circle, the angle here is 3 pi over 4. And so there you have it. These are our two important boundaries. And so now, if I were to put this back into the equation, I know that r, since we're doing dr first, we know it's from 0 to 1, and the theta is between 0 and 3 pi over 4. And so from there, we can then easily solve this double integral, just like what we've done before. And so with this one, what we can do is we can see that we can use substitution. So we can let u equals to 1 minus r squared. So du would be negative 2r dr. Isolate dr, we get negative 1 over 2r du. And so if I were to put this into here, I can factor out the negative 1 over 2, and this becomes square root of u. And then we have the r, but remember we also divide by r, so the r cancels out. So we just have square root of u du, right? Instead of dr, we now have du, and then we have d theta. And if you want, we can put that in brackets. And then for the boundaries, we can also change that. So for 0, if we plug in r equals to 0, 1 minus 0 is just 1. And then for our other boundary, we have 1. So if I plug in r as 1, we get 0. So then now I can solve this. So I focus one integral at a time. And for this one, if I were to calculate this, this is essentially the same as u to the power of 1/2. So if I were to integrate this, I get u to the power of 3 over 2 times 2 over 3. And don't forget our boundaries. And so if I were to do that, I then again simplify my answer. I plug in u equals to 0, that's just 0, minus 2 over 3 times 1 to the power of 3 over 2, which is just 1. So we have minus 2 over 3 d theta. And now we only have one integral left, so we can just solve that. So negative 2 over 3, if we integrate that, we just multiply by theta. And then if we plug in our values, we then get negative 2 over 3 times 3 pi over 4 minus 0. So to simplify everything then, I can cancel out the 3, and I get negative pi over 4. And then from there, I can also cancel out the 2 over here. And so this just becomes negative here, and our final answer is pi over 4. So that's how you solve this problem. That is our volume of the solid region W in 3D space given the inequality. So that's how you approach this problem. And so thank you for watching. See you next time.